So before we look at MG1, let us look at yet another design problem, right. So you are currently operating on a system, let us say this is a packet queue, right, this is 100 Mbps, and then you find that the queue lengths are large and the system capacity definitely has to be improved because your arrival rates are increasing. So you have two choices. You can of course simply make this a 200 Mbps link, we saw that the last time, but I can also add, but let us say it is impossible to go by a 200 Mbps link, right, only fixed capacity is available, so you simply have to buy one more link of 100 Mbps. So I am adding one more server, I am keeping my queue constant. Or so this is my lambda, right, this is my lambda, and let us say that my lambda I am splitting by whatever means into two streams of so I have two separate queues, so packets are split at the entrance to two separate queues. We see this in banks also, right. Only thing is in India you never know what kind of queuing system is used. You go to the bank, is it one queue or multiple queues? The guy will be shouting please follow one queue, but always the shortest queue they will just simply go and stand, right. So we should try to model that one too, right, multiple queues with where people always find the shortest queue to join. So what is the effective performance of that system? So then you will essentially balance at some point everything that is shortest queues will grow longer, and then right. So that we will see if I can, this book does not have that example, right, where customers choice is based on the queue length. So this is called arrivals with discouragement, where you discourage arrivals based on the queue length. Now which of these two would be better? This is another question, right, separate the input or separate at the service time. The variance of weight variance would be more. How about just mean will be the same, or mean will be this expected to be the same, okay, but the variance will be different between the two. Any other it's not really intuitive, but you just want you to think, right. Is better to have a single queue or two separate queues? Single queue.
So what are we trying to get better at?
We just want to see which will give me better performance in terms of response time. That is the user only cares about that, right. So you are saying one counter is not enough, you go to the banker says fine I will put two counters, then the question is should I have a single, there is assume that this is infinity, there is no, right, this is both mm1 only, so it is either mm2 or two mm1s. Two separate queues are better, one queue is better, okay. So some of you have seen that, some of you have not seen that, are trying to guess. We will go through that and then see, and then we will search for the intuition as to why, right, one system is better than the other. So for now we will simply let us say lambda equals 50 Mbps.
The last two examples.
So first I want to get them numbers, then once we see that numbers tell us this is what is happening, then we can, then they should be able to go back, because right now they are undivided, those who have not seen this problem before are not sure which way it is going to go. So we should give them that, first look at the numbers, then see why one should be better than the other, right. So the MM2 system, this is a rho equals 0.5, right. So we did this already yesterday or on Wednesday. So EF or P, everything was 1 by 3, right, P naught was 1 by 3, this thing was 1 by 3, right. E of NQ was also, wasn't it? Oh, rho was 0.5. Oh sorry, we should make this equals 100, right, okay fine, we will keep the same example, 100 by 200, right. So rho is 100 by 200, that equals 0.5. for the same 0.5. Okay, so E of NQ is this, and then what was E of what will be E of R? 13.33. What did I say, milliseconds, nanoseconds? It will be microseconds, or I did 100 Mbps, right? So it will be so just milliseconds at 100 Mbps link, and I am only looking at right per bit. I am not even talking about packets and all that. So one bit takes 1 nanosecond, right? So one bit takes 10 nanoseconds. Okay, so this is looking at per bit as a delay metric. So it should be nanoseconds, right? Because lambda is in 100 times 10 power 6 10%. So nanoseconds is correct. Okay. Huh? Okay, let's get conclusive answer on this. Since people are still in, how can, when I am sending at 100 Mbps, how can one bit take anything more than 10 nanoseconds? That is the 1 over mu is 10 nanoseconds, right? So the rest is queuing delay. Okay, then my 2 ones. So now my lambda prime is 50, mu is 100, and rho is, we will just call it dash dash to differentiate the two. Rho is basically also 0.5, rho dash, right? So E of R is 1 over 50 actually we are microseconds, isn't it? Because 50 times 10 power 6, then 10 power 6 goes up, and then 1000, no sorry, yeah, because I am multiplying by 1000 above. Okay, so alright, do these numbers agree with everyone? Second number is easy to compute, right? 1 over 50 into 10 power 6 better be 20 nanoseconds. So therefore this also got to be in that range, but it is less. So those who voted for MM2 can now feel a little better. But your theory that the mean will be the same is not holding good, right? Why? Because if you look at the MMQ, one is you look at the Markov chain itself, right? The return rates are faster for at least some of the states. Return is at rate 2 mu for all states, not all but the first state, everything is returning at rate 2 mu. Here rate is always returning at mu, only thing is my lambda is reduced to lambda by 2, right? So therefore customers, the effective service rate is better in the first system, MM2 system, because it is 2 mu, that is one. And the second intuition that we have tried to convince ourselves before is that it is possible that there will be let us see, that a server is, that a particular queue is empty and the server is free, and there are waiting customers in the other queue, right, based on the randomness of arrivals. So therefore one server might not be used for certain duration, that P0, right, whereas in the other case the server will never be empty as long as there is a customer waiting to be served. The single queue, the server will never be idle as long as the queue is not idle. That is another reason why you will find that first system will essentially perform better. So single queue is always better.
But sir, in this particular example,
MM2 mu, MM2 will be 2 mu if you remember that Markov chain. In the second case it is mu, but your rate is, the arrival rate is lambda by 2, right. So it, but the other explanation is that the possibility of waiting, right.
in this case, sir, MM2 will be better than that single queue system of not lambda by 2, lambda mu only.
No, actually that single system MM1 with 100 Mbps will be the, with 200 Mbps will be the best. This will be better than the, yeah definitely, yeah naturally, yeah this will, these two will certainly be better than that, right. Yeah, these two will be an improvement, right. So here if I were to give you 100, what's going to happen, this is a right, unstable system. I cannot operate 100 Mbps with the first with the basic system, right. This I cannot, lambda equals 100, right, means the system is unstable, which is one of the reasons why we said we want to increase the capacity, because lambda is approaching so close to mu that the lines are getting very long. So that is why we wanted to redesign. So therefore these two will be an improvement. So then the other problem we saw that day was, is an MM1 queue with 2 mu better, right. So finally that we showed that, so ultimately what the best way to do is to double the server capacity. So if you remember, the companion problem was, I said this is 2 mu, right. So if there is an option to actually simply double the line capacity or double the server capacity, then stick to a single queue. So this is what queuing theory tries to tell you, right, in various systems. So if you look at a network, then this is the application. Or if you look at a CPU, right, better to go to 2 CPUs share, servicing processes, or is it better to have a single CPU, or just double the clock cycle, or the whatever that you try to do, right. So but it's always impossible to simply double the clock speed, right. So you have to then look at 2 cores, and then you look at whether you want to have a, think of it as a processor, right. Processors are threads being executed by the CPU, this is ready queue, and instead of better to have one common ready queue than to have 2 separate ready queues, one for each core. Okay.
In the multiple queues case, is there just one arrival process lambda, and then the decision is taken based on which queue is shorter, right?
No. This is random. This is purely probabilistic. Yeah. So this does not depend upon the queues. Yeah. This is not dependent on the queue lengths. That I'll have to go and see what. If you consider the queue lengths, yeah. So this is random. That's why it's right. So this is randomly selected, or uniformly random, okay. But now one important thing that I have not talked about is that this is a Poisson process, right, and I have split that probabilistically into 1 or 2 more streams. Why should that also be a Poisson process? I am making that assumption here, right, which yeah, with probability, some probability pi, whatever be the distribution. So that is the property which I have not stated, but that is an important property which we are now sort of stumbling upon, right, which I think in one of your sample exercises I said prove that, okay. So merging of Poisson streams and splitting of Poisson streams essentially results in still a Poisson stream, right. So multiple Poisson streams at rates respectively lambda 1 through let us say lambda k when combined result in a So this is again a convenient assumption which is it is nice, because if you look at, say for example, queues, right, when there are if you look at one output queue of a router, so this is our picture of a router, okay. So router will get several packets from various input line cards, right, and they are all destined to this particular output port. So packets from this queue will, this port will come to this queue, from this port to this queue, and so on, right. So when I have several, each of these are Poisson streams. So independent Poisson streams, each of them at rate lambda 1, lambda 2, and so on. Then the effective arrival that this queue sees is sigma lambda I, and that is also Poisson. That is why I can use my MM1 assumption, right, when I merge different Poisson streams.
Same is true when you split them, right?
Yes, yeah. and these are fundamental properties of Poisson processes that we can look at some standard textbooks, and likewise splitting. I am saying stream, but whatever, Poisson process, right, as a stochastic process. So if the input is coming with a rate lambda, and then based on some probability, right, and which is fixed, so P1, P2, let's say PL, so the probability P1 will go to this, this will go to one queue, for P2 it goes to another queue and so on, then the respective queues will see the Poisson process with rate lambda P1, lambda P2 and so on. So that is why that splitting example we saw before makes use of this fact, that even though I am splitting but with equal probability, so it is simply a coin toss, it does not depend upon the state of the queue, so it is state independent. Questions on this?
So suppose we, in the case of two MMQs, we make an arrangement where we decide to feed the packets to the empty queues. What would be the result? Is it going to be better system or?
Oh, which
MM1 queues. We have a two MM1
okay.
queues, like
Do you mean state dependent?
Yes.
Queue length dependent. Queue length dependent, will that be in theory better? So you always go join the shortest queue, right?
Because at times what will happen, the both of them will become balanced, even if infinite queue.
But there is still a non-zero probability that the service times for two packets might be so short that they finish off and then they become empty, and then there is no packet in that corresponding queue because the guy already joined the other queue. This queue jumping is not allowed, right? So if you don't allow queue jumping, then you are stuck in the queue that you joined.
So once you are in, you are in.
Yeah. So therefore there is still that probability that the second queue also, right? So you might be balancing the two queues. That we can, if there is a closed form, I will try to find that. If not, that we can simply simulate, right? When we go to our simulation part, we can simply simulate that state dependent jumping, right? So you simply look at the current state of the two queues and take the shorter one and see if that is. Because shorter does not mean that the service time on average will be less, right, but the instantaneous service times could be fairly large, because that always happens, right? You go to the bank, you pick the shortest line, definitely something is wrong with that line, that guy is going to take forever, right? So that is why nobody goes there, it is the reverse that happens, okay? Nobody goes to the shortest line because that guy is going to get a DD and that is it.
It's like, it's not like only I am thinking, even everybody before me thinks the same way. We all jump to that side, and then now we see this is a shorter queue. Then we can keep on having.
This is after joining the queue, you mean? Yes. Yeah. Okay. Yeah. That okay. I am not but this is our third variation you are talking about, right? So one is at the joining time, and the other is keep going back and forth with some finite probability of staying in this queue or going to the other queue, right?
Wait.
Yeah, or you could have like a load balancer that runs in the, which is what distributed systems try to do. You find that this queue length is longer, you simply migrate jobs to be run on the other processor. That also no, I think we have to find out. Yeah. I have not seen it. Yeah, all these things are easier simulated than solved. Solved with post-form expression. Okay, so we will stop, but I will just give you. So we will look at this MG1 server, right? So we have done MM1 so far. We will not today, next week. And this MD1. MD1 is particularly interesting in at least networks because you are talking of deterministic packet lengths. So fixed packet lengths, especially when ATM systems were being discussed, there you have fixed packet lengths. MM1 is more for for telephone systems. It is not exactly suited for routers because packets are never exponentially, do not follow the exponential distribution in terms of length. So we will do that. Then yeah, we will do this MD1 with vacations. And the reason we will do the MD1 with vacations because that is a special case of TDM. TDM can be modeled as an MD1 server with vacations, and you can get a very nice closed form solution for that. That is why we would like to do that. And then I am sorry, oh, what does vacation mean? What vacation means is that server, in our example so far we have what is called as a work conserving server. As long as there is a customer, it is going to serve the customer, but that as humans we never do that, right? We always tend to take vacations or breaks as we call in the service sector. So in this case again it is not only server taking break, but even if you look at a machine, right? So machine will be constantly servicing jobs, and then you bring down the machine for maintenance, right? And that maintenance duration can be fixed, it could be variable, it could be because of repair also, right? Suddenly it has to be repaired, so the time to repair is again not a fixed time, that is also exponential, it can follow general distribution. So in that context what happens during that busy maintenance period, the system is idle, customers are waiting. So how do you characterize that? So with in the presence of vacation, what is the expected waiting time and delay and things like that, right? That is why this vacations comes in. It is not because this is true in case of machine scheduling and things like that, right? And so then we will go back to that slotted aloha, that example that we looked at, right? That is also there for your project implementation. We look at a different approach to model slotted aloha. Just because I worked it out 20 years ago, you have to suffer through that, right? So we will come back and model slotted aloha as a Markov chain, but not in terms of the number of users, but in terms of a single user. So just to give you another way of trying to model that system, you can also get to the same set of results by modeling the behavior of a single user in the context of other users. It is a little bit more involved, but you still have to solve a set of equations to get it. I think that is probably where we will stop. Then the GM and all that stuff, the results are there in the textbook, so I will just we will stop at that point with respect to the open queues. Then after that we will move into queuing networks. Okay, so far it will be all single queues. Then we look at how do you interconnect queues together, because if the queuing networks is actually if you look at a real computer system, right? The example that we saw before in the tutorial also, which all of you skipped, where there is CPU feeding to device queues, then it comes back, right? So those are the kind of systems where you need to get some idea of what is the throughput of the system and things like that. Let's switch gears to MG1. MG1. MD1, after we do MG1, MD1 is automatic. So okay, yeah, so cease all discussions on the test. Let's come back to so for the MG1, the arrivals are Poisson like before, and the rate of the arrival is lambda arrivals per second. As far as the service process goes, it can be any service distribution. There are besides the mean, in the case of exponential we knew 1 over mu is the mean, right? We knew 1 over mu squared was the variance, right, and all those things. So here we need, besides the mean service time, let us say you are just sitting at the bank and watching how long it takes to service each customer, right? So you can compute the mean very easily, right, just by the sample measurements. You can also compute the second moment, right, which is simply the square of all the service times divided by the number of customer requests that have been serviced. So this is a second moment of service time. So it so happens that with these two we can quickly derive the MG1, same thing, waiting time, all the other metrics that we want to look at we can easily derive. Okay, so we will let so the rho is the same as before. It used to be lambda by mu, where 1 over mu was the average service time, right? So here it is simply lambda into EFS, that's all. the definition is the same as before, ratio of the or product of the arrival rate into the average service time. Okay. So then we have some other definitions. So Wi is the waiting time of the ith custom. Fair enough, right? Customer I comes in, how long does the customer I wait in the system before getting service? This is a waiting time, right here. Now when the customer ith customer comes in, right, two things are possible. One, the server is busy or the server is idle, two possibilities, right. So if the server is idle, then this notion of residual service time, right, that is what this RA represents, right. This is a residual service time seen by the ith customer. So if a customer is being serviced or served by the server, what is the remaining service time for that customer? Say J is the customer being serviced. So that is this what I see as I enter. So Ri will see the customer J who is being serviced, the remaining service time. That is what this Rfi is supposed to represent. In the case of exponential service, that is always 1 by mu, right. Whatever point you look at the server, the customer service, it is always 1 over mu because of the memoryless property. But in the case of other distribution, that need not be the case, right. So therefore there is some remaining service time for the current customer being serviced. That is what RFI represents. That is if the server is busy. If it is not busy, it simply goes to 0, right. There is no, this guy will get served. If the server is idle, ith customer will automatically get serviced by the server itself, and therefore there is no waiting time, itself goes to 0. Okay, so that, so if server is idle upon arrival, then Ri goes to 0. Ri goes to 0, Wi also goes to 0, there is no waiting at all, right, for this particular customer. Ri is just the customer that is getting serviced, that is all. Wi is the other customer, Wi is the total waiting time. See, I come to the queue, there are 5 customers already in the queue, there is another guy getting serviced by the server. That guy getting serviced by the server, that remainder of the service time is the Ri. Wi is the time that is going to take for everyone to get serviced, that is all.
Okay, so the time taken, the queue plus the service time.
Yeah, time taken in the, for the remaining customers in the queue. So when we derive the Wi, you will see that why this Ri is special, right. This thing is,
Even if the server is idle, then
is the server,
remaining.
there is no Ri. The server is idle, which means that the queue itself is idle, right. There is no, the queue is empty rather, right. If a new customer comes in and finds the server idle, what does it mean? That there is, right, that at that point in time there is no customer to be serviced. Otherwise the server would have been servicing the customer in the queue, assuming it is a work conserving queue.
So Ra is basically part of 1 by mu, right?
In the case it is a part of 1 by mu, the fractional, in the case of exponential, the Ri is always 1 by mu because it is, right. So because whatever time you look at the system, it is going to be there. So now okay, let us look at this. So then we will say Si is the service time of the ith customer and then Ni so Ni is the number of customers in the queue waiting for service. At the time that I arrives. So this is looking at the system, looking at the system from I's perspective. Okay, so if you represent this as my queue, right, there are some people waiting, there is some customer j, right, who is getting serviced, okay, and then I is, this is the ith customer, right, assume that the customers are numbered sequentially, okay. So there is I is the ID of the customer just now entering the system. So what will be the ID of the customer at the head of the queue? There are ni customers, right, so therefore it is I minus ni, right. So now we have this the waiting time for customer I is given by the residual time for this customer j, right, this fellow, which we say we call it Ri because it's Ri is the, it's not the time that I sees when there is somebody j is getting serviced on the system. What is the remainder of j's service time is what we denote as Ri, and then I equals right, right. So it is simply adding up the service times of all the people in front of me plus the residual service time for the customer under service, that is all. It is not a very hard derivation, right. So these SIs are random variables, right, or will have, so they follow whatever distribution that we are seeing, and this ni is independent of this SI, right. So if I take the expectations on both sides, again I am skipping some of the, if I take the expectation for a sum of random variables, right, then it will be simply product of the corresponding expectations. So E of Wi is E of Ri plus, this is the expected number of customers in the system when I enter the system, right, into simply E of S, right. We said that taking expectations on both sides, S is nothing but the service time, and what is the service time average, right, in the long is simply E of S, right. So this ni is the number of customers that were in the queue when I entered the system, right. So now we know there is, from Little's law, E of ni is the queued customers, right. So what is that? Lambda into E of, right, we called this NQ before, but I am using a slightly different notation because this is why I am taking this from another book, an old book, Bostikas and Gallagher from MIT, right. So that is a 1982-87 book. So some of the terms except this x I am changing that to EFS, everything else is following that notation, right. So by Little's law, and then we can assume that, right. So as I approaches infinity we assume, right. So this is basically the average waiting time. So E of W, which we have seen before, right, is essentially, we call that E of R simply drop all the i's as I goes to infinity, right. So therefore there is an extra EFS that I forgot, right. So Ni is this one, then EFS is also there, but it so happens as lambda ES is 1 minus is rho, right. So this is basically rho into EFW.
So if this server doesn't take vacations, R will always be 0.
Yes, server takes vacations and it will be simply that plus vacation, average vacation time.
No, no. So what I'm saying, if it doesn't take vacations,
R should be 0, yes, yes. Okay. So basically E of R is now related to, or E of W, so the average waiting time seen by a packet, right, is simply the is proportional to the residual time of the customer, average residual time of the customer that is seen, so divided by 1 minus rho. So that is first part of our derivation, right, this is one. Questions on this? Okay, part 1, this is part, right. So this is the R is basically the W equals R by 1 minus rho.
Actually, I still didn't understand what R means. Because we go to the previous page.
Okay.
So the waiting time is the sum of
fellow.
service times of the previous packets.
Yeah. Of
plus
all
the
this
time
is,
you take after that.
this guy arrived at some point in time, right. So let's
Okay.
say that how do we represent this in Q? Okay. So this customer J is currently in service. Okay. If I were to draw this in terms of a time axis, this is when J started service. This is when I arrived. Okay, and J's finishing time is this. This is of the time that is going to be taken to service J, right? S of J, the total service time, right? And so the time that is remaining is what I call as R. That's all. The remainder, right? Waiting time in the queue. So I have to wait until this guy gets finished, all the people in front of me get finished. So the average of that is simply the average number of customers I will see in the queue when I enter into the average service time, right. If I am average, I will see 5 people when I enter, and each customer is going to take 10 seconds on average. Therefore the average time to get people in the queue who not yet started service is simply 50 seconds, right. Okay. So now what we need to do is somehow figure out what this E of R is. To get to the E of R, we use a slightly different way to write it, right. So let us say that I define R of tau. Okay. So there is a time varying function called R of tau, that is the residual service time at time tau. So I pick some random time tau and see either there is a customer in service or not in service. If there is no customer in service, then the this R of tau is 0. If there is a customer in service, then it is simply the remainder of that customer service time, right. So I can plot this with respect to tau, right, R of tau. Let us say that up until this point, right, this is my, say, 0. Up until this point there was no customer to be serviced. Then suddenly there is a customer to be serviced. Okay. So what will, when the customer starts service, let that customer service time be, say, S1, right, the customer number 1. So R of tau will become simply S1, right, because the instant, what is the remainder service time? S1, residual service time is S1, and then as t or tau increases, this keeps on decreasing linearly, right. So it will come down to 0 and it will take S1 time units. And if there is yet another process or job waiting to be serviced, let us say that takes time S2. So it is like a sawtooth graph like this. Okay, and assume that there is for a little while there is no customer to be serviced, then after that it goes like this, it goes like this, and so on. Okay, so then I am interested in the some time instant t, right, at which point time we want to do some sort of analysis. Okay, so up until this point t, let m of t be the number of service completions, right. So how many customers were served in the interval 0 to t. Okay, this is S3. So okay, this continues, right. So but I am interested up this is some point t. Okay. So now if I take the area under the curve, right, and divide that by t, isn't that my average residual time, E of R? Right, the average residual time is simply R of tau d tau from 0 to t, right, divide this by t, right. So that is the R. I am simply summing up R of tau at every instant of time and then dividing it by the total time taken. That is my average residual time, right. Each R of t is instantaneous residual time. I am adding them all up dividing that by the total time interval t, length of the interval t, that is the average residual time, right. Not a very hard thing to accept, right. I see kind of trying to pull a fast one or something, no, Whistler. Okay, and so what is that? Just look at this, I am just right, this is half Si squared, that is all. So this is 1 over t I going from say 1 to m of t half Si squared, right. Simply the area of all the triangles, which is half S square Si squared, and then simply adding them all up to this point. So this now we can make a little bit interesting by saying this is m of t by t, then I have this Si squared by m of t. So what is m of t by t? M of t by t is the number of completions, average number of completions, right, and in an MM1 system, an MG1 system with infinite queue, the number of completions is equal to the number of arrivals. Throughput is basically equal to lambda as long as rho is less than 1, right, that is the balance, because only if I have 10 customers coming per unit time, then they will leave the system again. If you look at the number of customers leaving, it is also going to be 10, so lambda is going to be equal to mu, right. So therefore this is basically lambda into, so mt by t is the throughput of the system or number of customers leaving the system, which in a balanced system with rho less than 1 is always going to equal the number of customers arriving. I cannot have more customers leave the system than arriving, right, that will be very suspicious, it has to be equal, and I cannot have, right, on average number of customers should be, can be maybe one customer less might be depending on the observation interval, but in the long term we simply say that it is equal. Yeah, we forgot the half, we'll put the half here, so we will do lambda by 2 into, so then what is this sigma S squared by m of t? E of S squared, right, that is the second moment by definition. E of S is simply S1 S2 by n, E of S squared is simply S1 squared S2 squared divided by n. So this is, so that is why the results now depend upon rho, which depends upon E of S as well as E of S squared the second moment. Yeah, by the ith packet. Yeah.
Shouldn't it be only dependent on the jth packet that is being serviced?
Yes. So in the we are taking the mean
average over all the packets from 0 to 2.
Yeah, that is one derivation. This is another way of also looking at the residual time. What will in any packet on arrival, what is the residual time it is going to see, right? This is the long term mean residual time is what you are computing, right? Yeah, in the second part I am deriving it, there I defined it that way, but it also can be defined in this way and derived in this way, right? What is the mean residual time that any customer arriving at any point in time will see, right? So if a customer comes here at this point in time, yes, it will be instantaneous will be 0, right, but what is the long term average over some interval that you are measuring of this value, that is what you are computing here. So remember all of these are means, right, so therefore it is not instantaneous values. Okay, so therefore E of W equals lambda then the other things are all straightforward, right. E of R is simply E of S so with this basic result we can also figure out what MD1 is. We can go back and see, right, all we need to know is the second moment. What is the second moment of finite distribution? Second moment of MD1, not 0, second moment is not 0, variance is 0, second moment is simply E of S squared, because all values will have E of S, E of S, service time is constant and therefore E of S is simply one value, right, there is only one value whatever it is, some will just say E of S for the sake of, therefore second moment is simply E of S squared, so it will be lambda E of S to the whole squared. So you will have lambda ES will give you rho into service time divided by 2 into 1 minus rho, and that will, so what we will see is that for the least waiting time will be seen for MD1Q. You cannot do any better than that, because that is the one for which coefficient of that COV is also 0, variance is going to be 0. We will derive this in terms of the book has a slightly different formula. Raj Jain's book has slightly 1 plus the coefficient of variation whole squared, that we will come back and derive.